Hello everyone. Today, I will discuss with you vector algebra. Initially, my discussion will focus on the dot product of vectors, how that product is defined, what are the properties of that product, how its value is computed, and the discussion is supported with sample problem for you to easily follow the concept. Let's start with the discussion of dot product. Imagine that we have here two intersecting vectors A and B, having magnitudes equal to AM, BM, respectively. And the angle between them is angle theta. Suppose that we have here the vector A, whose magnitude is A sub m. This vector is intersected with another vector, vector B, whose magnitude is B sub m, and they are separated by an angle equal to theta. Let us imagine that we have here theta. The dot product of the two vectors A dot B is equal to the product of the magnitudes of A and B multiplied by the cosine of the angle between them. Thus, this can be written as A dot B equals AM BM cosine of the angle theta. What about that product of unit vectors? Unit vectors being also a vector. However, these are vectors having a magnitude equal to 1 and specifying a specific direction. Let us imagine that we have I, J, and K be the unit vectors of the directions of the positive X, Y, and Z axes. Hence, let us have these directions. Let us imagine that this is our I, here is our J, and here is our K. The three unit vectors have or are separated by a 90-degree angle. By definition, when we say I dot I, how do we express this value? The definition of the dot product states that it is equal to the product, the magnitude of the vector, multiplied by the magnitude of the other vector times the cosine of the angle between them. If we are talking of the same direction, meaning the two directions are separated by an angle equal to 0. And if we are also talking of unit vectors, their magnitudes are equal to 1. Hence, if this value shall be substituted in the formula for I dot I, then that gives us a value equal to 1 times the cosine of 0, which is also equal to 1, will give us a value that is 1. So from this computation that I have presented, we can make a generalization that the dot product of two parallel vectors is equal to 1. Knowing that the dot product of two parallel vectors is equal to 1, then we could also say that J dot J is also equal to 1 and K dot K will also be equal to 1. You may ask why I have presented the dot product of unit vectors, because later on, as we go on with this discussion, we will be applying that very important value of the dot product of two parallel vectors. How about the dot product of two perpendicular vectors like that of IJ, JK, or KI? Let's start with the perpendicular vectors I and J. By definition, I dot J shall be equal to the magnitude of I times the magnitude of J, which are both equal to 1, multiplied by the cosine of the angle between them which is equal to 90. Since cosine of 90 is equal to 0, then we can say that the dot product I dot j shall be equal to 0. With this presentation, we can make a generalization that the dot product of two perpendicular vectors is equal to 0. Similarly, we can also say that the dot product of I dot k will also be equal to 0, as well as the dot product of j dot k. Let's study this time the properties of dot product. What are they? It is said that dot product is commutative. How do we explain that property? When we say commutative, we say that the dot product of A dot B is also equal to B dot A. The position of the vector in the dot product multiplication has nothing to do with the resulting value of the dot product. Hence, dot product is commutative. Second one, the dot product is associative. What do we mean by associative? Let's take a look at this dot product. If we have m times the vector A multiplied using dot product by n times the vector B, the result shall be equal to mn times the dot product of A dot B. How are we going to explain this property? Whenever a vector is or has a coefficient that is scalar quantity, then the scalar quantity are associated first before they are multiplied with the dot product of the two vectors. Hence, m times A dot n times B is equal to mn times A dot B. And that is what we mean by the dot product, which is associative. Number 3, dot product is distributive. When we say distributive, we can distribute the vector to the term inside the parentheses when they are multiplied using dot product multiplication. As such, if we have A dot the quantity B plus C minus D, then A shall be distributed with B, C, and D. Hence, the value becomes A dot B plus A dot C minus A dot D. And this is what we mean by dot product is distributive. With the definition of dot product and the different property, we can generate the other definition of dot product. Let us imagine that we have here the vector A, which is expressed in vectorial form, such that A is equal to AXMI plus AYMJ plus AZMK. And let there be another vector which is also expressed in vectorial form, such that you have BXMI plus BYMJ plus BZMK. Now, the dot product of the two vectors A dot B, when substituting the vector in vectorial form, then this becomes the product of AXMI plus AYMJ plus AZMK dot the quantity PXMI plus BYMJ plus BZMK. Take note that the first term of the dot product consists of three quantities representing the magnitude of the components of A in the X, in the Y, and in the Z direction, while the second quantity has the second term have three quantities representing also the magnitudes of B in the X, in the Y, and in the Z direction. If we will be applying the property of dot product multiplication, which is distributive in nature, then we can distribute AXM to each term of BXM, BYM, BZM, as well as the second term to the three other terms of the second quantity. Hence, we can say that this product, when multiplied, will produce AXM BXM times I dot I. This product, when multiplied, will produce AXM BYM I dot J. While this product, when multiplied, will produce AXM BZM I dot K. If the second term shall be distributed with all the three terms of B, then we shall have AYM times BYM, AYM times BXM J dot I. Similarly, this product shall be equal to AYM BYM J dot J, and this product shall be equal to AYM BCM J dot K. Now, if the third term shall be multiplied individually to the remaining terms of B's, then this product becomes AZM BXM K dot I. This will be equal to AZM BYM K dot J, while this one will be equal to AZM BZM K dot K. Now, looking back at this product and analyzing and applying the properties of that product, knowing that the dot product of two parallel vectors like I dot I being equal to 1 will reduce to AXM BXM. Similarly, this term AYM BYM multiplied by J dot J, knowing that J dot J is the dot product of two parallel vectors which is equal to 1, then this can be this will reduce to AYM BYM. Similarly, this term which is equal to AZM BZM multiplied by K dot K, knowing that K dot K is also equal to 1, this will reduce to AZM BZM. While the other terms having that product of two perpendicular unit vectors, as such we have AXM BYM times I dot J, knowing that I dot J is equal to 0, then we may cancel this term in the equation. Similarly, with this term equal to 0, I dot K, then we can also cancel this term in the equation. If this term will also be analyzed, then that term will also be 0, and this can also be cancelled in the equation. Similarly, this term having the product J dot K also equal to 0, then this can also be cancelled. Furthermore, this term which is equal to AZM BXM multiplied by K dot I being equal to 0 can be cancelled. Similarly, the last term which is AZM BYM multiplied by K dot J will also be equal to 0. Now, simplifying the remaining equation, we can say that the other definition of that product can be defined as the sum of the products of their respective components. Meaning, if we will multiply the respective components of the two intersecting vectors and then sum up their products, that gives us the dot product of the two vectors. For us to easily understand and to follow the discussion, let us have this example. Given two forces F having magnitude of 600 and directed from A having a coordinate of 2, -1, and 4 to B having coordinate of 4, 1, and 3, and another force Q having a magnitude of 560 and directed from A toward C having a coordinate of -4, 2, and 2. We are required to determine the following. Letter A, the dot product F dot Q. Letter B, the angle between F and Q. For this video presentation, I will only focus my presentation on the solution to letter A. The solution to letter B will be reserved for my next video presentation. Let us now identify the given in the problem. In the problem, we are given the magnitude of F having a magnitude of 600 Newton and directed towards A and B. We have the second force here having a magnitude of 560 and directed from A to C. The coordinates of the points are given: A at 2, negative 1 and 4, B at 4, 1 and 3, and C at negative 4, 2 and 2. And from here, we are required to determine the dot product F dot U and the angle theta between F and U. In order for us to solve for the dot product F and Q, and because we are given the magnitude of the force and their direction, then from this given alone, it will be easy for the components, for the magnitudes of the components of the force to be computed. Hence, the magnitude of the dot product can easily be computed using the definition that the dot product is the sum of the product of their respective components. Hence, the idea of solving for this dot product is to find for the magnitude of the coordinates of the two intersecting forces, and from there, we multiply the respective components and sum up to give us the dot product. So let's start with taking their magnitude. Let's start with solving for the components of the distance where F is passing. That is the distance between A and B, because F is directed from A to B. How do we get the distance? From our previous discussion, the distance can be taken from the components of the distance from which the force is directed. That is directed from A to B. Therefore, it is the components of the distance between A and B. And we can solve for X as the coordinate of B minus the coordinate of A, that gives us 4 minus 2. And that value is equal to 2. We also solve for the value of Y, that is equal to 1 minus negative 1, gives us a value of 2. And for Z, that is the coordinate of 3 minus 4, giving us a value of negative 1. From here, we can solve the distance between A and B. Solving for that, using the formula that the distance shall be equal to the square root of x squared plus y squared plus z squared, and substituting this value here, that gives us the square root of 2 squared plus 2 squared plus negative 1 squared, gives us a value of 2. Now, after computing for x, y, and z in the distance and knowing the magnitude of 600, we can compute for the component of force F in the three mutually perpendicular axes, using the definition that the magnitude of the component of the force is proportional to the component of the distance between the 2 points from which the force is directed. Hence, that can be substituted in this formula such that F sub x sub m is to x, as F sub y sub m is to y, as F sub z sub m is to z. And that is also equal to F sub m is to the distance between A and B. Now, substituting the value between the value that we have just taken, then that gives us this value, and from here we can compute for the magnitude of the x component of 400, the magnitude of the y component at 400 also, and the magnitude of the z component at negative 200. And that's for the force F. Now, for the first force Q, let us solve for that. Okay? Let us solve for the components of the distance where Q is passing. Similarly, we do the same. We solve for the distance x, and that is equal to, directed from A to C, that is A to C. Okay? The magnitude. We are also given the distance at value equal to 6. Similarly, we solve for the value of y, which is equal to 2 minus negative 1, and that gives us 3. And the value of z, that is 2 minus negative 4, and that gives us a value of negative 2. From here, we can solve for the distance between A to C, substituting that value in this formula. So you can solve for the value of the distance, which is equal to 7. and from which we can solve for the magnitude of the component of Q in the two mutually perpendicular axes by substituting that in this relationship, where x, y, and z are these values, and Q sub m is the magnitude of Q at 560. Now, substituting that value, we have Q sub x sub m divided by negative 6 is equal to Q sub y sub m divided by 3 shall be equal to Q sub z sub m over negative 2 shall also be equal to 560 divided by 6. And from here, we can solve independently or individually the value of the components, such as Q sub x shall be negative 480, Q sub y at 240, and Q sub z at negative 160. Now, after computing for this magnitude, we are now ready to compute for the dot product. The dot product being the sum of the product of the respective components, meaning the magnitude of the product of these two, the product of these two, and the product of these two. Now, simplifying, substituting that value, we shall have 400 representing this, and 480 that magnitude. This 400 represent this magnitude, and 240 is that magnitude. Negative 200 is this magnitude, while negative 160 is that magnitude. Now, simplifying that value, that gives us a value of negative 64,000. I hope that with the short presentation I have prepared for you, you are able to understand the meaning of that product and how that products can be computed. In my next video presentation, I will show you what are the applications of that product. If you have questions about the topic, you may subscribe to this channel and post your comments so that I can answer your questions in my next video presentation. Once again, thank you for